All right, this is AP Calculus, Unit 3, Lesson 5. We are doing curve sketching today. Again, we are on Standard H, and Standard H, that is graphical analysis. So, continuing on, this is our last time doing Standard H. We have some derivative graphs. Go ahead and make sure you have everything here copied down, and then we can do the knockdown. So pause it now. All right, so moving forward, x squared, what does that look like? If you know it, go ahead and graph it. I'll go ahead and start doing it here too. You need to know the name of this. Well, I guess you don't need to know, but it's nice to know the name of this function. It should look like a smiley face, and I'm doing my best to sketch what it looks like. This shape is called a parabola, and the type of function that this is called a quadratic. So let me write that here because it is kind of nice to know. This is called a quadratic. I'll just write quadratic. So each of these I'm going to go down. I'm going to say that this is the, maybe I should do this in a different color, that this is the graph of f. Graph of f. This is going to be the graph of f prime. We're going really far today because we're going to do the graph of f double prime and the graph of f triple prime. All right. So if I have a quadratic and I take the derivative, and before I even do that, is this a positive quadratic or a negative quadratic? If you answered positive quadratic, you're correct because it's smiley face. A negative quadratic would be a mountain or a rainbow. So the derivative of a quadratic is what? If you answered linear, I should do a different color here. You are correct. Linear. And what is that linear going to look like? So I'm going to actually use my line tool because now we're starting to care. Come on now. We're starting to care where our lines are exactly. So this one is going to be directly through the origin, and the slope, I don't really care what the slope is. It's going to be right about through there, but through the origin. All right. Actually, I do care what the slope is now. I take that back because we can actually calculate that. What is x squared? The derivative of x squared is, it is 2x. Then I know my slope now. My slope is not just any number, it's slope of 2x. So it looks a little bit steeper like that. All right, so what is f double prime of x? If I take the derivative of this function, what do I get? I get 2. And from there, I can graph what does that look like. Y equals 2. And hopefully you remember what that looks like. Y equals 2 is a flat line at the y coordinate 2. What type of function is this? Do we know the name of him? This is called a constant function because it's just a constant number. You might be thinking linear because of the line, and I guess you're correct in saying that because it is a line, but more specifically, it's a constant. All right, what happens if we take the derivative of 2? Derivative of any constant is 0. So y equals 0, what does that line look like? That is a line that looks like this. And what type of graph is that? That is going to be called the zero graph. So I'll just say that this is called 0. Just need to know names of things here. All right, so today we need to learn how to go backwards. If I give you a graph of f prime, I need you to be able to figure out what the graph of f looks like. So what does that mean? And before I go too much farther, I will let you know that the notes will only be about a page today, if that, as long as you can get 4 graphs in a row like this. All right, so I want to look at some examples here. So let's title this examples. All right, let's get 4 more graphs down here. So these are not associated with the graphs up here. All right, so when I take a look at these graphs, I'm going to give you the fact that I have a constant function. So let's give you this. I have the constant function, and I'm going to say it's going to be down here like this. All right. So I know that this is constant. And what type of constant is a positive or negative constant? Is it below the y-axis or above the y-axis? And you should answer it's a negative constant. The values are negative. All right, now if I go backwards from a constant, what do I end up with? And you can clearly see that is a linear function. But what type of linear function? Where does that go? So I know that this negative constant, it has a slope that is what? Well, if this was a constant positive, it had a positive slope. This is a constant negative, so it has a negative slope. So my line will have some negative slope. And if I knew exactly what value this was, I could tell you exactly, well, roughly, no, I could say exactly what value the slope would have, but some negative slope. So we don't know where the y-intercept is. It could be here, it could be down there. We don't know, but it has a negative slope is the main point. So the main thing to take away from here is that a negative constant, if I go backwards, and I guess I should have done this at the very beginning. If I go backwards, and you don't know that I'm going backwards because I haven't written it here, but this should be the graph of f prime, and this is the graph of f. So if I'm going backwards here, from a negative constant, that is a negative linear. That's what we want to write here. So negative constant turns into a negative linear. All right, so that was our first example. We can label that number 1. Let's do our second example over here. And I'm going to have one more slide for me, and hopefully that will get you guys to exactly one page. Still give you enough room for the summary. All right, so what happens now? So I'm going to say that this is the graph of f still. Graph of f, and this is going to be the graph of f prime. Graph of f prime. Okay, so I'm going to tell you that I know that there's this line for our linear function. This type of curve. And whenever I say curve, just think of, oh, he's talking about the shape of that line. It's another way to describe it. So I've drawn this curve, and it happens to be a straight curve, which doesn't really make sense. But anyway, what is this thing? What type of function is this? What type of curve? If you answered linear, you would be correct. So this is a linear. Linear. I want to draw in blue. Okay, linear. And is it a positive linear or a negative linear? If you answered a positive linear, you're correct. And maybe I should do a little circle around the positives and negatives so they don't look like just weird tick marks. So a positive linear, if I go backwards to the graph of f, what is that going to look like? And that's a little bit hard to think about. So maybe we should analyze what's going on right here. Let me make a different color here. This mark right here. Something is happening. The graph of f prime has crossed the x-axis. In other words, another way of saying that is that the height of this graph is 0. When f prime equals 0, when the height of f prime graph is 0, what does that mean? What have we found? What is that definition? This is a critical value. Not only is it a critical value, but it is a relative extrema because I've switched from a negative to a positive or from a positive to a negative. Now we know it's a relative extrema, so I guess I can label it, but it's not really important because we need to know what type of relative extrema it is. Is this a minimum or a maximum? So what goes from a negative to a positive as I go left to right? So think about that. What goes from negative to a positive for f prime? Is that a minimum or a maximum? If you answered minimum, you are correct. So I know that on my graph over here, for my graph of f, I have a minimum somewhere on this left-hand side. I didn't label exactly what this point was, but let's say that point, again, is right there. So some minimum. So a positive linear does turn into a positive quadratic. So I can go ahead and label it because I know what it's going to be. This is going to be, and I don't know where my graph is going to be, I'll write it up here, positive quadratic. Quad. And if you want to know how to spell quadratic, I can spell it out here on the left. This is quadratic. Okay, so it's going to be some shape like this, and it's going to be positive, so it's a smile, not a rainbow. And the minimum, the lowest point it gets, its vertex, is going to be at this value. It doesn't mean it has to hit it. I can go up and down as much as I want. I can draw you two different examples if you want. So here's the first one that comes to my mind. So I have a function that comes down. That's the lowest point it gets to, and then it starts to come back up. There is a quadratic. All right. Another way of saying this, another graph that I could have drawn, and I can draw this with, let's go with green. I could have drawn it all the way up here. As long as the minimum is right at that point, you're fine. It can be either of those two graphs. It can be any of 1,000 graphs. We're not exactly sure because we don't have the actual equation. We're just practicing the sketching, going from f prime back to f. All right, so I'm going to go on to the next slide, so pause me if you need to. We need to do 2 more examples. All right, so I'm going to label these. This is going to be example number 3. This is going to be example number 4. Since this is my last slide, maybe what I can do here is back up here, and I can move these so they're a little bit easier to see. I can move these down here, and maybe a little bit farther apart. We have plenty of room here. All right, so this is going to be number 3, and this is going to be number 4. All right, again, you want to start by labeling these what they are. So we're always going to have the graph of f, graph of f prime, graph of f prime on the right, graph of f prime, and the graph of f prime. All right. Wait, no, not an f prime, f. There we go. So let's give something harder. I'm going to start with a graph of f prime that looks like, I'm thinking a quadratic. That's good. So my quadratic is going to look like this. All right. That looks good to me. All right, so graph of f prime. So what do the heights of this graph represent? The heights, so if I say the height here, this point represents what on the graph of f? What does that represent? That represents, well, it represents f prime because heights are the exact representation of whatever the title of the graph is. So heights are f prime, which means the heights here correspond to slopes here. All right, so using that, let's analyze more what happens at this x-axis. Similar to what happened in our previous example, when we cross the x-axis, that means something very special. I'll do it in red again. So right here and here, I've hit the x-axis. When x equals 0, or DNE, what is that? That is a critical value, CV, CV. So there's 2 CVs here. And is it a relative extrema? Is this a function relative extrema? And you have to ask yourself, what is the definition of function relative extrema? And that means that you have f prime switching from a negative to a positive or a positive to a negative. And in that case, both of these are relative extrema. I'm not going to write that because more distinctly, I want to know if they are minimums or maximums. So ask yourself, as I move left to right for this point, am I becoming a minimum, or am I a minimum, or am I a maximum? So I'm going from a negative slope to a positive slope. What goes from a negative to a positive? Give you a few seconds to think. And the answer here is minimum. So now over here, this is another critical value. And I'm going to ask the same question. It's a relative extrema. Is it minimum or max? And it's going to be the opposite because I'm going from a positive to a negative. Girls, I'm recording. I have the hat on. So this is going to be the opposite. This is going to be a max. I'm going from a positive slope to a negative slope. So how do we represent that with the graph of f? How do I have a minimum over here and a maximum over here? Well, what type of function turns into a negative quadratic? I should have asked that question, but this is a negative quadratic. What type of function turns into a negative quadratic when I take the derivative? What? So I'm coming back up here. I don't have an example here, so I can't really figure it out, but you can remember this from a previous lesson that if this is a negative, Okay, let's actually do this in blue. This is a negative quadratic. This is a negative quadratic. This will become a negative cubic when I take the graph of f, a negative cubic. So a negative cubic means that I don't start in the bottom left and go to the top right, because don't write this, but that would, if I stretched out the cubic, it would look like this, and that's a positive slope. Instead, I'm going to start up here in the top left and go to the bottom right. That looks like a negative slope, and I just have to add the peaks and valleys. So a negative cubic, I want to have the minimum at, I'll go ahead and make my red marks again. So this is going to be my minimum, this is going to be my maximum. They correspond to this graph over here. So my minimum, I'm going to have some sort of valley down here. So I'll make this a valley, and then I can fill it in later. And then somehow I'm going to have a maximum over here. So I'm going to have a peak over here. That's all I really know. I guess I do know some other things. I know that in the quadratic over here from our last lesson, that where it changes from a positive slope to a negative slope, that represents the second derivative, which means this point right here is an IP, an inflection point. But that's really hard to graph on a graph of f, so we really just need to connect these two lines so that they make sense. So coming back to the graph of f, so I can make this a little bit drawn out to come up here and connect. I could do this better, obviously. And comes back down here, and this also comes back up. So this is a negative cubic, and we have our answer. All right, and we should label these two. So up here, this point was our relative max. It's not the max, I'm just lazy here. This is our relative max, and this is going to be our relative, I'm not gonna write relative, our relative min. All right, moving on to our last example, and then we can do our summary. So I want to start with the graph of f prime. Let's do, let's go as far as we can. This is going to be a little bit of a stretch, but I think you girls can do it. So if I go ahead and make my graph, I'm going to make this graph a cubic. I'm going to make this a positive cubic. Do you remember what a positive cubic looks like? Cubic. And you might be thinking, oh, Mr. Sandell, that was a negative cubic, so just switch it. Instead of going valley, peak, do peak, valley. And I would say, yes, you are correct. So start with a peak and then end with the valley. So I'm going to just kind of sketch this out here. So start with a peak, come down here, end with a valley, and we have our positive cubic. All right, so now we have to analyze our critical values here. Always look at our critical values where it crosses the x-axis. Those help us immensely. All right, so when I look at that, and maybe I should have extended this line a little bit, and I can do that with technology, hooray. Extend this line a little bit. So how can I analyze this by looking at the critical values? Well, I know critical values are where I cross the x-axis, so let's go ahead and mark those out. So critical value here, here, and here. Remember, the definition of critical value is just where f prime, this is f prime, is equal to 0. And since it has a height of 0, that is a critical value. All three of these are relative extrema. Why is that? What's the definition of relative extrema again? That's right, it changes from a positive to a negative, or a negative to positive, or more succinctly, it changes signs. So all three of these are relative extrema. I'm not going to bother writing that. I just want to know if they are minimums or maximums. So same question as always. If I have a negative f prime and I turn into a positive f prime, is that a minimum or a maximum? The answer here is a minimum. And then it kind of alternates back and forth, because now I'm going from a positive to a negative. It has to be the other one. That's a max. And when I go from a negative to a positive over here, that's going to be a minimum. So it just kind of flip-flops all the way through, unless you somehow have a discontinuity, as we have seen in our homework sometimes. Oh boy, now trying to go backwards. So a cubic. Remember, a cubic is something of the form x cubed. And remember when we took the derivative, so I'm going to say this going forward was taking the derivative, so d dx. When we took the derivative, this turned into some form of x squared. Technically, you could say 3x squared, but some form of quadratic. And then when we took the derivative again, d dx, the derivative again, we had something linear. Do you notice the pattern with the powers? What if I go backwards now? I'm going backwards to the graph of f. So I'm going backwards such that, okay, I can draw that line a little bit better, such that when I take the derivative, d dx, I get x cubed. So what type of function is that going to be? And you can clearly see the pattern is x to the fourth. But what does that look like? Well, maybe you can see the pattern in the graph. I have a hill, and then I have a hill and a valley. So when I go backwards, I'm going to have a hill, a valley, and a hill, or a valley, a hill, and a it goes back and forth. I forgot which one I just said, but anyway. So we have 3 different turns. I have 2 turns here, 1, 2, 2 times where the slope is 0. Now I'm going to have 3 times where the slope is 0. And now we have to ask ourselves the question, well, we already kind of know this, but if this is a positive cubic, what is this going to be? A positive or a negative? And I need to go back to blue. This is going to be a positive, and the word for it is quartic. Positive quartic. Q-U-A-R-T-I-C, quartic. Just means the 4th power. So for a positive quartic, that means that I need to, and just, I guess we'll have to take my word for it, but it ends up with both arrows going towards infinity. So usually when you have something to the even power, if the left endpoint and right endpoint end up, like our parabola ended up, that was the even power, then that means that it's going to be positive. And maybe I can write this more succinctly. So even powers point up. Okay, all calls coming up, go away. So even powers point up. When positive, the inverse is true, so, well, not exactly, but the even powers point down when negative. So you can write that as well, but I think it's kind of clear by writing this. And then for odd powers, even powers, I mean like x squared, x to the 4th, so quadratic and quartic. And odd powers, the way to tell if they're positive or negative is if you stretch them out. You can kind of see this function. If you stretch them out, that they would, let's make an assumption. So powers, assume that they're positive. If they're positive, then when I say start, I mean on the left. So start, bottom left, bottom left. Pen is dying right now. Start in the bottom left, end on the right. That's what I mean by end. End, top right. Top right. Which means that if it's positive, it looks like this. Because this started in the bottom left, it came all the way down here to infinity, if I continue drawing that line, all the way in the bottom left and went to the top right. That means it's positive. And vice versa, if it starts in the top left and ends in the bottom right, that means it's negative. Just a quick way to memorize that. So coming back here, that means if it's an even power, they need to point up at the end. So it needs to point up at the end, it needs to point up at this end. I know it's positive. I also know that there's a minimum here, maximum here, and minimum here. Let's label those points. So I have a minimum here. I'm not going to label it because it might run through that point. But a minimum here, a maximum here, and a minimum here. So what is that going to look like? And as long as I have a minimum, I'm doing it correctly. So I'm going to have my minimum here. So it's going to come down here like this. And then I need to have my maximum up here. So maybe the slope needs to not come up as steep. It'll come up slowly to a maximum and then finally come down to a minimum down here and then back up to a maximum. This graph definitely could have been better. I could have made it cross the x-axis, but it doesn't necessarily need to, right? We just needs to have the maximums and minimums. So let me label those to make sure that I actually got them all. So this one was supposed to be a minimum. This one is supposed to be a minimum. This is supposed to be a maximum. And this one was supposed to be a minimum. All right, so that was the hardest one that I'll be giving us. So if you have this one nailed down, you are ready to go. And that is how we do our lesson. Yeah, I don't think there's anything else that I have to add. So go ahead and do your summaries.